So again, welcome to Machine Learning for Material Sciences. So this one will be like the final technical session that we'll have only ML related, but we'll have how this today's ML is used for material sciences. Hopefully, some part today and then some part next class. Fine. But this is again, as Professor Sen has been telling, so all these lectures we are expecting, these are typically out of the course's scope, but you may expect some here and there questions, so it is important in that sense for the exam. Technically, not to remember stuff, but some logical questions might come. Hmm. So with that, yeah, and one final thing is like we are studying this. Uh, uh, Fine, I'll cover that later maybe. Okay, so welcome everyone again. I think the words that have been written on this particular slide, I think most of you have some or the other idea. Typically on the lines of generative AI. Yes, so I think all of you have been using, let's say, ChatGPT and Claude, let's say, or Meta's WhatsApp, whatever Meta AI in WhatsApp and Gemini. So all of them are form of generative AI. I have told you a little bit difference, like on general prediction and generative. Uh, Generative would be a prediction would be more like given certain like part of the sequence, you're trying to predict the next one. Generative would be more like I have given you a set of examples. Generate something which is different from this set of example, but should be similar, having the characteristic. Yeah. So predicting what will the cat do next can be like a prediction problem. Generation would be like, generate a cat. Given you have seen 1,000 cats, generate a new cat. So it is a new thing, but should be of those samples. In the both the cases you are predicting, it's just minor difference in vocab, let's say. Yeah. And typically the generative AI, there are multiple parts of it. One of those parts which is very useful and powerful for image for a particular sense or vision, let's say, that can be videos and everything else, is your diffusion. Yeah. So I think you might have heard DALI, let's say Mid Journey at least. And if you ask ChatGPT to create pictures, it uses diffusion in the backend, and same with Gemini and everybody else. Yeah. So for images, and if you not only images, like anything that has this spatial structure in the data itself, diffusion is the way to go right now. So currently, whatever we will be covering is like state of the art for generative models, specifically for pictures per se. But the picture you have to understand there is a special relationship between arrangement of the items. Hmm, fine. And okay, so now like in the image for only for the image, like what have been the major paradigms that we have heard about this in a few like few of the previous lectures, at least the words itself, at least in the advanced series part. So one of them is basically GANs, so generative adversarial networks. It's basically a game that two players are playing. One game is trying to generate a fake image, the other one is trying to tell if it is a fake or a real. So generator is trying to beat the like the discriminator. Discriminator is the one that tries to detect between real and fake, and the discriminator is trying to beat the generator. So though both are playing games against each other. Yeah. Uh, GANs have been absolutely very popular. Around 2013 onwards, they were popular, and majorly because they were super fast to generate stuff. But the problem was training them was not nice, I would say. Nice is a very understated word, but it was very unstable. If you had generated a GAN output, you would be like probably will tell you you're very lucky. Yeah. And and generally something happens is called a mode collapse. Mode collapse is where basically either all the losses become zero. So that means the entire, I'm not sure if I have seen you the figure. So the loss function of gradient descent is like this curve. So assume if this entire, like this curve becomes a flat surface, then doesn't matter where you go, basically you will still reach to the same value, but that might not be the optimal at all. But that is the mode collapse. Yes. This happens in some time. If given some time in future comes and it's a proper ML class, we'll discuss more. But mode collapse happens. Right? So basically, there is no training possible at that point. If it reaches to a very flat surface, you don't know which area to go, because even if you go left, right, or north or south, you are still stuck. Yeah. Now next comes VAE, the variation autoencoders. These were again popular also. What they do is basically, instead of, they're saying like instead of asking everybody to look at the entire picture and then create another picture equivalent to it, what you can do is you can play with the latent space. Yes, so instead of looking at a 1028 by 1028 space, let's say that is a pixel of image, let's say size, you can play with a very small set. Hmm? Now, what is that? Basically, you encode the entire image to a very particular, like, dense latent space, and that is called latent space. And then you reconstruct from the latent space itself. Right? I will show you one diagram. Uh, so the idea, this could do very like a nice training, was very stable. But the problem is the moment you reduce the 1028 by 1028 to, let's say, 28 cross 28, right? So we tried to cramp all the information that was there in 1000 cross 1000 to 20 cross 20. Then obviously we are losing some information, right? And generating from that 20 cross 20 an entire 1000 cross 1000 image was very difficult. So often the outputs that were produced by VAs were blurry. Hmm. They were not pixel perfect, let's say. GANs were like very nice, like the pixels were very nice, matlab the pictures that were generated were very nice, right? So then GANs and VAV is continuing, like some one on this, some one on that. But now the current, basically, how do I say, the new kid on the block is basically diffusion model. So they provide you the best quality that we have, and they provide very stable training. The only problem is the sampling is slower, but we'll come about that. But as the state of the art, any image generation model that you have will be using this diffusion model. And this is just a nice figure to show you how, like, all those paradigms that I discussed. So GAN is basically, if you look at there is a X is like the input, and X prime or whatever you see, those are the output that is getting generated. The first for the GAN, if you look at that, so X goes into, let's say, a discriminator, it says it's real or fake. Then from Z, another area, it generates basically one new image. VI basically takes an image, encodes it into a very small space. From that small space, you try to decode. Yeah. Now the flow-based model, and remember in GAN, discriminator is only used while training. It has no relation with generator as such. It just helps to make sure the generator is better. Hmm. And flow-based models, this is something similar to what VA does, but a little bit more in differential equation format, let's say. Diffusion model also do that, but flow is similar, like X, you have a flow of X, let's say, and then it goes to Z, and then Z goes to, like, you have an inverse function that takes you to X prime. X prime will be like a generated output. And then currently what you have is diffusion. What it says is basically we gradually add Gaussian noise and then we try to reverse. I'll show one more example, which looks better maybe. Fine. Uh, So yeah, this you can have it. This particular graph, figure, you can have for your reference in your mind. And next, so now what are the diffusion models, right? So what it says that you imagine taking a photograph, okay? and you gradually start adding static noise. Fine. I hope you might not remember the old TV when you like the antenna probably was not connecting, the static noise used to come on the TV itself. So imagine you keep on adding those static noises slowly, slowly, slowly. Yeah. And as you are doing it slowly, 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 at a point, eventually you will forget that what was the original image. Like for example, here the dog was visible, and at the end you see the dog is not visible, right? It's just like a salt and pepper image. Hmm. Now, let's say you also learn the image you also learn another model, let's say, which understands how to reverse. So if you give me a salt and pepper image, the static noise, then I should be able to go back and produce the image for you. Right. That's exactly what diffusion models do. So one is you add a noise and make sure it reaches to a very noisy area, from where you cannot even think of what that particular image is. Computer understands a little bit more than us because computer does not deal with overall visual inspection as such. Yeah. Somewhere there is an information what it should be. Yes. But for us, visually, we cannot say anything if you look at the last image. And then you also learn the process of reversing this one. So it has two processes. One is a forward process and there is a reverse process. Okay? So mathematically, I'll go. So the core idea again to learn to reverse a gradual noising process. Right? So you add noise and you learn how to reverse that, remove that noise. So there are two processes. One is destroy the data, like forward process, destroy the data by adding noise. This has no learning involved. You're not learning anything. You're just adding noise, yes, by simple maths. And then reversing, that is where you learn. So you learn how to denoise step by step, yes. And here neural networks are used. Right. And so once we understand how to reverse the noise, basically we can take a noise and produce new images. Uh, Basically now we understand from noises we can go to new images. So we are basically generating from noise, we are generating new images. Okay, so that's basically diffusion model. And so maths basically says, so if you look at this equation, so every time when we add basically Gaussian noise at each time. And typically here, if you see beta t will be the noise schedule, controls how much of noise to add at each step. And this is typically very low value, 0.001 to 0.02. And what the formula shows is basically the new image, like the QXT. XT is the time of the new, that is a new image, let's say, image at time t, as compared to the previous time t minus 1, will be the slightly old image plus some amount of noise, right? So every time the new image is the old image plus some amount of noise. The old image could have is basically the previous noise added image plus amount of noise. Yes. So this is a recursion process. Yeah. The only nice property, or not the only nice property, let's say the nice property that we have in the entire formulation is that we can jump, let's say, jump directly to any xt. Hmm. So that means if you look at the nice property here, so we can sample xt from x0 directly. We don't need to do it like, I don't need to find x1, x2, x3 to continue to xt minus 1 and then x1. Rather, I can just from x0 itself, I can sample xt. Fine. So this formulation allows us to do so. Sorry, I hope this is still visible. And fine. So, and this is what basically typically helps this particular rule, that we can jump to a random xt from x0 directly, and we don't need to look at the intermediate steps, is what basically helps. Okay. So now what we have, let's look at a little bit more deeply. So first one is the forward process, fine. So it's xt, then like if you look at the formula, so what it basically says, we're adding normal noise, fine. It's just pure noise, okay? It's getting added to the original x0 plus the epsilon that we have, fine. And this is the closed form solution of going to any xt. Fine. This we are not traversing one by one, rather any xt. Okay, and okay, sorry. And there is also the way to schedule the variance. So we have, if there is a normal, that we need to have some variance attached to it. So we can have linear, which is like way simpler. Uh, sorry, and works nice. But there is also cosine variance scheduling. This one is what is currently preferred per se, let's say, and it works very nice for images. Fine. But the difference is basically linear would be linear in this. Cosine will slowly increase the noise addition. So in earlier steps, and or you could take it to the later late steps. Initially, it will start at slow, then increase the noise addition process. That's all it does. Now, what is the reversion? Okay, so reverse distribution is where the learning takes place. But here, what we say is like if you want to go from xt minus 1 given xt, the goal is to go to xt minus 1. That means I have a picture at, let's say, timestamp t, and I want to go back to xt minus 1. So noise has been added from xt minus 1 to reach to xt, but I want to find how do I go back from xt to xt minus 1. Fine. Now with this, what do we do? So we know if the disadvantage here is when the while training we would know, but while basically when the logic is getting applied, so the original x0 image we would know something during training, like so reversing will be super easy if we knew x0. Yes, but the point is in there are two things here. So while training we know x0, but while actually doing generation, when we do actual generation, our xt becomes a complete noisy image. So if you see, look at the last image in this particular pipe flow, that is the noisy image. Once the training is over, what we will basically give the input to the diffusion model is the last image. From last image, we have to figure out what should be the output. So at that particular state, if I knew x0, of course, I could have applied Bayes rule directly and we could have got. But the problem is, like, I do not know the x0 when I'm doing generation, right? So what do we do? So we train a neural network that can do two things. Like either that can directly find out what my x0 is, given xt, what would be x0, or it could find out what my noise was. Fine. So that means, so if I found my noise, then I can take the xt image, I can subtract the noise, and then I get my original image. So there are two things, right? So from xt, I can go to x0. I can train a neural network that can, okay, from xt, you take me to x0, or otherwise, give me xt, and I will find out what the noise is, and then xt minus the noise will give me the x0. Right? These are two ways. And typically, what we do is generally we try to learn the noise. Like the formula might be a little bit scary, but intuition is pretty simple. So it just says that given a noisy image, just predict what the noise was added and then subtract it. That's all it does. Uh, Fine. Now, okay. Now what do we do? So what we say is like if you want to go from xt minus 1 to xt, we say, okay, there exists a neural network probably which can do this. We have a loss function called elbow. Fine. Uh, this is on variational part. I will not touch it very well. What it basically says that we can close the we can what we'll find out is basically the distribution of xt and distribution of x0. What is the gap between these two? And then we will try to minimize this. Fine. Distribution in terms of, you could think of like, let's say, easier thought is number of black pixels and number of white pixels, let's say. And so the number of white pixels and black pixels in the noisy image should be very close to number of black and white pixels in, let's say, original image. That is of course not going to solve the entire problem, because there is special correlation also, right? Because I can have top half white image, top half, let's say, black image, and a chessboard could be the original image. So even if both of them have the same distribution of white and black pixels, they are not the same image, right? So there is another thing that is involved, that is spatial correlation. That means the white and black, every white has to be surrounded by all black, and so on and so forth, let's say. But let's say this one was the initial thought. So given a loss function called elbow, I parameterized my going back process with a neural network, which could basically find the loss. And once the loss is found, I will just subtract it from the image and find out. So, this worked really, really well. Yes. And one of the initial model that worked on is denoising diffusion probabilistic models. This was a paper that was in Europe's 2020. But what it says is the same thing again. So it takes a real image, picks a random timestamp, appropriate amount of noise is added, uh, and then here the process is the other way around. It shows the but x0 if you want to go from forward, and you train a network that predicts a node, and you repeat it for okay. So diffusion one additional is you need a lot of data, so and you do it millions of times, right? So and then you can find. Then how do you sample? Let me just go to it. So first part is training. So you sample x0 from the real data. You first sample some form of, let's say, basically your timing. So if I have to do it for, let's say, 100 times, let's say my entire time period is, let's say, 100, 0 to 100. I could either do in like steps of 1, steps of 5, steps of 2. So that will determine how much jump I am making. So that is basically sampling T. Epsilon is the noise that I'm sampling. What I'm counting is like my forward XT, like how my XT is going to generate it at the time of T. And my goal is to minimize this particular noise. And the sampling is basically how we start with the pure random noise. We ask basically question, what noise do you think it is here? Right? And then basically we subtract, right? And we keep on repeating till we get a clean image, fine. But remember, like the idea here is not to learn to denoise at all levels. The network learns the structure of the real image basically. Hmm. I'll show you one more figure which might be a little bit more clear. Now, as I told you, like the entire learning and forward process, they go fine. But majorly the loss function, let's say the elbow function is there. It looks at distribution of, let's say, the original image and the x0 versus xt, right? And I told you, if we just look at the black and white pixels, right, it could be like a chessboard versus a top half is black and bottom half is white. They have distribution will be the same, but in the picture they need to have, like, correlation needs to be there special. That means white pixel has to be surrounded by the black pixels and black has to be surrounded by white, and so on and so forth. That mapping, like to understand this spatial correlation among this distribution, image related models are used in the neural network. So one of those nicer models that was used in the first diffusion models was UNet. Yeah? You must have heard about this in earlier lectures. So UNet is basically it's a neural network. This looks like in a shape of U. That's why it's called UNet. So what it takes is basically takes one image, let's say 1000 cross 1000, and it starts downsampling it. Basically 1000 cross 1000 will look like 500 cross 500, then 200 cross 300, then 100 cross 100. Then again from 100 to 200 cross 200, 300 cross 300, 400, 500 cross 500, then 1000 cross 1000. So eventually it starts with 1000, reaches to very low, and then again it goes to 1000 up. Yes. But there is one more thing that is involved, that is called channel. Basically 1000 cross 1, let's say, if it is, the moment you downsample, that means becomes 500 cross 500, the number of channels also increases. If you see here, uh, I don't know if this one is visible to you. So if it is like 164 is, let's say, if these are number of channels, let's say. Now in the next one that becomes 128, the next is 256, 512, and 1024. So these are, let's say, the number of channels, right? And again it goes back and finally it comes to, let's say, whatever the original was, right? So this is original UNet. And like why this was originally unit. Okay, so originally unit was used to do medical image segmentation. This is like very popular in that field. But why is it useful in diffusion? First is, of course, like the same input resolution and same output resolution. So we're good because we require that. Now, the skip connections that are there, skip connections are basically this. We talked about skip connection a little bit earlier. So if you look at this, 1000 cross 1000 in input is connected to 1000 cross 1000 in output. So some details that could have been, as we are compressing the image to 500 to 100 to 20, some details would have been lost. That happened with, let's say, VAE. Here we are trying to pass that information like 1000 cross 1000. Okay, some information you pass it forward to the output 1000 cross 1000. Fine. So this is the skip connection that has been given. So this basically preserves finer details. And then we can have multi-scale processing also. Like what it does is basically we 1000 cross 1000 looks at very finer details. 20 cross 20 looks at very low level details. Yeah. Fine. I'll just give me a moment. I'll just turn the light on and come. Yeah. Okay. Fine. And then this is okay. And so again, so just repeating, encoder decoder will preserve spatial information, which was earlier missing in my thought of like original thought of just matching the distribution. Now skip connections will help in multi-scale features, and then time embedding is also required, but that's part of this rather than that. So this one, the time embedding that is T here is given. Those are more for the time embedding. Basically, we are attaching a time to a particular picture. Fine. Sorry. Now we have created pictures and it understands to reach from one picture to another. But how do we assign a particular, like, how do we sequence the pictures? Like, if one picture, after noise, it is this picture, after noise, it is this picture, after noise, this picture. Specifically, because we can do this, I hope you remember that nice property. Because we can jump to any time step from x0. That means from x0 I can jump to x4, I can jump to x8, I can jump to x100. Now how do I remember, like, or how do I tag x5 or x10 or x100 and tell the machine learning model, let's say computer, that this was basically the 100th, the image after 100 addition of noise. That is basically done by time embedding. So we add some information to the picture that basically tells, okay, this is this time, right? So one of this time embedding, actually this comes from transformers also. So we use something called a sinusoidal position encoding. There are other types of encoding as well. What it just says that if a picture is generated and given some time t, there is some more additional information that is added. Uh, we don't need to discuss entirely in depth, but that's the entire goal. And once you attach this information to xt, computer will understand, or the model will understand, this is the 100th image, this is the fourth image, this is the second image. Fine. Okay. And what is important? Because network needs to know, right, how much noise is present. Basically, which time step, the time step here decides how much noise were added. Yes. Okay, so now what? So now we go on to a little bit. I will go through this just like a little bit quickly. The formulas are there, and you can go over later also. But this will be just like what has been done till now. Yeah. So one of the things that has been added is attention mechanism in diffusion. I hope you remember generative AI. On generative AI, one of these things is like ChatGPT and LLMs and all that stuff. They're basically more transformers dependent. And one of the like tech, or let's say methodology behind transformers is basically attention. Yeah. The other side is basically the images, and the images basically run through diffusion, which are basically you add a noise in forward, and try to learn a neural network that can take a noisy image or a noisy output and bring back a real image, right? So what people first try to do is basically, can we use the attention in the transformers that we got, can we apply it to basically diffusion? Fine. And typically this is useful because attention also had, because attention earlier, when transformers were introduced, that solved the problem of things that are people keep forgetting. So before attention, like before transformers, there was recurrent neural networks. It took like words in sequence to generate the next word. But the problem is, if you take words in sequence, you start to forget earlier words little bit. So here, the same thing. So can we use attention to solve the forgetfulness of diffusion models? Yeah. And this is one of the DIT thing. So what it does is basically, you have diffusion model. Instead of using the unit and everything else, you could use basically an entire transformer instead of unit, which will automatically have this attention timestamp embedding done, which will solve that problem. I'm skipping over it, like details if required will come later. The next thing that is there is score-based model. This one also you will hear a lot. I think like one of our papers uses this one. What it does is basically says, this is a little bit advanced, but even if you don't understand fully, I'll try to see what we can do. What we say is basically like the score will be gradient of log probability. Fine. Uh, it basically says that, okay, so while you are learning, you don't need to learn everything, but maybe wherever you see there's a high probability of gradients that are moving in this direction, the other probability areas you can ignore, just move to the high probability areas. Fine. Eventually diffusion tries to learn this particular score. Score is this, and our earlier, if you look at what I told, like you want to basically, through diffusion you're trying to predict the noise, not the x0, and then you subtract the noise. So here predicting this score is equivalent to predicting the noise, right? And there is like proper mathematical work to show that predicting this noise epsilon is equivalent to predicting the score. So this was basically useful by Song and Norman. And yeah. And the next thing that came is basically DDIM. The initial paper that we started with is called DDPM, let's say denoising diffusion probabilistic models, that used UNet. Then time embedding also. We did better for diffusion with attention mechanisms. Then came score-based models, where you do maybe not look at all of them, maybe just look at the hypervalid regions. Then came DDIM. DDIM is another approach just to help like diffusion to work. So this particularly states that because we in diffusion, I told you that you have to do for millions of images, plus if the timestamp, that means if I have 0 to 100, I can go by 5 steps, then I will only do 20 images in between, or I can do 1 then 100, or you can do 0.5, that will make it 200. The more number of time steps you do, the neural network learns to basically, if you reduce the time gap, let's say time gap between two steps, that means the amount of noise that is added in the original image, let's say x0 to x1, will be very small. It will be way easier for the neural network to find this. But the problem is, if you reduce the time difference too much, then the number of steps it takes to reach the full noisy one becomes too high, right? So that means this sampling itself takes a very long time, right? So what it says, basically DDIM basically says, okay, uh, what you can do is, instead of doing 1,000 steps, you can do, let's say, 50 steps, yeah? And you can do it very fast. uh, what you can do is basically, it says that we can do a deterministic sampling process that still inverts the same forward process, right? This is one of the areas. that we can work. It's just DDPM, but with sampler, like faster sampling. The next is guidance methods. There are a bunch of methods in this. This is just one of the ways. I'm not saying many. So one of them is the guidance methods. Here, basically, what it says that you have the diffusion model, but you can have another classifier, right? Which basically sits and tells you you move to this class. So, for example, you are generating cat or you're generating animals, right? There can be another model which sits and tells, okay, you move towards cat, you move towards dog, you move towards horse, right? That's all about guidance. So that means there is some other model that sits and tells others to go here and there. So basically, we train one model for both conditional as well as unconditional, and at sampling, you would basically give a small prompt like thing, okay, go there and go here, fine. Um, you can have classifier free guidance also. We will come. One of them, the newer ones that are there, is latent diffusion models or stable diffusion. This is what generally is the backbone of current diffusion models that we have. Uh, Latent diffusion. They're saying instead of moving from directly image to image, can you move from latent to latent? I hope you remember latent. So it's like 1000 cross 1000, you have converted to 20 cross 20. Can you move from 20 cross 20? Can you create new 20 cross 20s? And then you again go back and create images. Hmm. So remember this conversion of big 1000 cross 1000 to 20 cross 20 is like a VAE encoder. I hope I'll just quickly jump there so that there is a flow. So if you look at this, like X is, let's say here is, oh, sorry, I'm not able to, okay. So I've selected the encoder part in the VAE. So it takes 1000 cross 1000. Your Z becomes 20 cross 20. From 20 cross 20, you are doing 1000 cross 1000 again. So here exactly the same thing. Instead of diffusion from one full picture to another full picture, rather we would have from latent space to another latent space. Fine. And this has been super useful. There is something called a clip. Not today, but if you hear the word clip, it's used here somewhere. Fine. This is stable diffusion, a little bit more rules. And then modern diffusion models. So basically, we have DALI 2, we have stable diffusion, we have ImageN, Midjourney is there, super nice. Video generation, again, we have a lot more commercial ones right now. Yes. Sora is there and all this. And for audio also, like because images are still there, but audio also, if you do like a spectrogram output, I think that looks like an image. Same with the materials also, but that is tomorrow. Matlab, on Friday we'll cover that. And DALI 2 is one of the little bit recent, so I'll just tell a little bit brief on top of it. So it's basically you can write a text. I hope you have used DALI 2. You will write a text, and from text it will generate an image. You must have seen that astronaut on a horse and like looking at the night sky, that particular image. So what it does is basically from text you move to a clip embedding, and then you from that text embedding you try to move to a image embedding. From the image embedding you run a diffusion model that will create you an actual image. Yes. uh, but I hope like this is so text to one like a middle term embedding that is called clip embedding. From clip embedding you go to final image. So given a text you can now generate an image. That's how DALI 2 was very far like very popular. And okay, so uh, now that an image has been generated, how do you tell if the image is good or bad? Fine. So there are few metrics that are good, like important. Like one is the FID. It basically compares the distribution between the real and generated image. Um, Lower is better here, or fresher in inception distance. And then inception score is there. Similar thing here, it calculates scale divergence between this. It's similarly a distribution but it's not a subtraction per se. In FID, we calculate the like the mean and uh, like like the I think mean and variance. But here we generally do a KL divergence between the distribution of those two. And precision recall always are there previously, and there is also clip score, which is basically cosine similarity between the clip embeddings of generated image and text. Instead of asking the question on the image itself, we ask the question on the latent, like the clip embedding. So, what are the applications? There are a few. We'll just go through quickly, not an issue. So, one of them is in painting. That means if something is missing in the image, you could in paint it. But I hope you are listening to this talk by thinking on the materials perspective as well, right? So, in painting is given a particular image. If some parts are missing, can we fill it up? Yes. Uh, this is done by, for example, you can add masks. That means you forcibly remove and tell them and give them a ground truth. So if this was, let's say, the original picture, I remove this part. I ask them, okay, what is this? I ask the model, what is this? So model learns to predict this particular part, and so on and so forth. That is done by random images. And in painting, what we can do, we can remove objects from this. I hope you in your phone, when you like a circle particular area, it removes those objects. Again in painting, again through diffusion. Image extension, for example, if you I don't know if Samsung probably has this. If you this, it tries to cover, add more sky, add more background, add more floor. Hmm. And super resolution. It takes a low resolution image, converts to high resolution. Fine. Uh, The next is image editing also. Like for example, there is a horse running and a person is sitting. You can change it to like a person on a zebra. Yes, those can be done. Like there are multiple algorithms for it. I just want to touch one more portion, so I'm a little bit hurried now. And super resolution with diffusion. Again, there are a few papers you can take a look. But the idea is again same thing. You take a smaller image. It's a 64 cross 64 image. You convert into a 1024 and 1024. Anything, I think, movies, if you see remastered movies and all those stuff, they're specifically using the super resolution. And there is also this satellite imagery. If you have, they specifically do super resolution on top of it to find out more details. Because you can get low resolution satellite images quickly than high resolution satellite images, because satellite needs to be staying constant to gather all the sense, all the lights falling on it. That is a slower process, and also there has to be no clouds and all. But rather you can take multiple low quality images and then use super resolution to convert them into high resolution. So photo enhancement, medical imagery, and like satellite imagery. So all of them. Yeah. The next part that I want to just touch, because we'll be covering some parts maybe tomorrow, matlab next class. So one of them idea is basically graph-based generating models. Yes. So we have looked at diffusion. So diffusion does it very nicely for pictures. The way it does is basically adds noise, and there is a neural network that learns the reverse one. Fine. Uh, so here now the graph based generation model. So why we should look at graph separately? Because all our molecules, proteins, social networks, all these graphs. Almost most of the real world things, they just generally they are most, let's say, how do I say, the best representation, not the best, let's say, the most apt representation as we can have is graphs. And why they should be treated different? Because it has a non-Euclidean structure, like size, then permutation, invariance, all of these come into picture. Distance notion is different. But traditional diffusion basically works on image. One pixel and one pixel, if there is a difference, we understand they are neighbors. But in graph, that is not the case, right? So nodes can be neighbors by connected only with the edge, which is an additional information that comes into part. But that still does not tell you anything about distance. Like uh, distance of two edges might not be same as distance of two edges somewhere else, right? So now what happens? So we have to basically change our diffusion model so that can understand graphs better. So we take input X, let's say graph will be designed by X and A. X will be basically nodes and the features of the nodes. So features of the node mean, if let's say this is a social network, every one of us who is in social network, let's say Facebook, we have some features. That is basically X. Combination of all our features, basically my name, my location, my phone number, my email address. If they are in the Facebook, then all of these individual items become my features. Then we have adjacency. Basically, if you and me are friend on social network, then we have an edge between us. So that is represented by adjacency. So again, so what are the size? Discrete structure, variable graph sizes, because the input image can be always 1000 by 1024. Let's say 1000 cross 1000. But if we have a like social network graph on LinkedIn could be smaller, Instagram could be bigger, Facebook can be even bigger, and so on and so forth. But the questions we ask are still the same. Now, permutation, invariance, and equivariance. So, like adjacency matrix, even if you permute anything with the adjacency matrix, the graph has to still remain the same. And then validity constants. For example, like chemical rules will apply. A double bond should always behave like a double bond wherever they are. Carbon and hydrogen can only have, let's say, covalent bonds, let's say. So those things has to be given as a constraint. Now, what can we do? So one idea is basically we can treat uh, uh, the graphs as discrete. Let's say we can relax the continuity, right? So we treat edges, discrete edges. Okay, so the one is the below one. Sorry, I started. So you define the forward process as discrete states. So that means every graph as an instance, we will treat graph as an instance, and instead of a Gaussian noise, we can add a categorical noise, and then we can uh, yeah, that's the measure in discrete. And continuous, basically, we treat the discrete nature as continuous, and then we discretize at the end, because at the end, maths will, whatever we observe, it's discrete. Like we finally see an instance of graph, not a continuous flow of graph, right? So we can treat from one graph to another graph. The internal process is continuous, that is one way, or we could do discrete, right? Instead of adding continuous noise, we add categorical noise. That means edge is present or edge is not present, right? So that cannot be edge is 50% present. That has no meaning in graphs. Yeah. Uh, because at the so either we tell okay, is being present 10%, 20%, 30%, 40%. That is from the starting to the end, but at the final we have to tell either the edge is present or not present. And the second one, basically, we are saying that instead of doing 10%, 20%, 30%, we always go in discrete. Edge has to be present or edge does not have to be present. Hmm. Fine. Uh, then diffusion on graphs, I told you like the same thing, but only thing, how do we treat graphs? Uh, uh, Now the next is graph neural networks. This one, okay. So in graphs, there are special types of neural networks that operate on graphs itself. Uh, and the key concept behind this is called message passing. So what we say is like if there are two nodes that are connected, this particular node will behave in a way based on its neighbors, right? We do the similar thing in images also, right? So images, we put a convolutional filter on top of it, which is a filter which is of a bigger size. So in graphs, we put convolution, we tell it's message passing, messages from all its neighbors around the graph, wherever it is connected with an edge, all those information needs to come. So if you look at this particular equation, that is what it says. If you look at the summation of M, that Mij is basically messages coming from my neighbors. So if I am Hi, let's say I am the ith node, I will gather all information that is coming from my edges, right? So, and that's how I will update my, let's say, values, right? Uh, just a minor, as in just have an overlook on idea, like, but you no need to remember this per se, because anyway, outside the scope of this. And now then graph neural networks for denoising exists. So what we do is let's say one of them example is digress. Digress is one of the papers in 2023, I believe. So here we use transition matrices for categorical diffusion, and then network basically predicts the clean graph directly, and it works really well for molecular generation, right? The major highlight was it handled this discrete node and edge types. Basically, if something has to be, let's say, uh, like atomic number, if we're trying to predict atomic number of a particular atom, so that cannot be, let's say, 1.5. No such thing exists. It has to be one, it has to be discrete. So in that sense, this handled it pretty well, the digress. There are other works also, let's say equivalent diffusion for molecules. This is another work. Uh, uh, Specifically in drug discovery, materials design, we will cover next class. And then conditional graph generation, because here we could also tell what kind of graph do you require. Similar to the pictures where you could write. Here also, you could also generate molecules with target properties. That means what is binding affinity? Is it a toxic drug or a non-toxic? And how much, let's say, new drug we are generating, will it bind to this particular protein or not? Right. So, and the same concepts of whatever used, like guidance is there. What can we do guidance without a classifier? And then can we do condition on top of it? All these are done. And specifically, you see they're modifying genetic molecules binding to target protein, modifying existing proteins to improve properties, as well as connecting molecular fragments. So all these are applications, and there are a few other like papers. You can take a look at all of them. There are more newer papers as well. So to give a summary, so diffusion exists. It basically does by adding noise to each step, and then from a noisy, you go back and find a real one. This is the current state of art in generating image. But what we see is most of the real world that we have are generally graphs, specifically like, scientific data, let's say also molecules, materials also, but that is tomorrow. Like Friday. And what is the difference? So image has a fixed grid, graph will have a variable structure. Noise here will be Gaussian, but what we have in graph will be categorical. We can do Gaussian also, but at the end, again, we have to discretize it. Here we'll have UNet. In graph, we will have GNN. And in like image diffusion, translation is there, the symmetry is translation. But here permutation variance is there. Like even if we like the nodes move around, it's still the same graph. Yeah. And output, basically this is continuous, and graph generally are discrete. Fine. So hopefully with this, some idea. So basically diffusion exists. You can generate new images from it. But there is also graph diffusion model where you can generate new graphs of it. Some applications, the entire point of this particular class was to tell you the existence of graph diffusion model, which is now very, how to say, useful in generating new materials. Okay. And probably we'll talk about one of those applications on Friday. So hope this gives us some background so that you are ready for the Friday's class. Fine. If there are any particular questions, I will wait. And the references for all the figures is this, and you can take this also post to learn a little bit more about diffusion model. All those maths that we talked about today are a little bit more detailed here. So if you want to go through how the derivations happen and everything, please look at this post. Okay, with that, I will stop. If there are any questions, I will take. Otherwise, we'll meet on Friday.
Yeah, is there any part of the sort of theory of graph-based models or diffusion-based models that you will that are left out that we'll discuss on Friday, or you are done with the model part?
Sorry, person, like probably.
Yeah, so I'm asking you, is the model part discussion of the ideas of the model, both diffusion model and graph-based models, uh, is that discussion complete, or you have something more to discuss on Friday? That's what I'm asking.
Friday we will discuss along that paper, whatever the theory small part is there, we'll discuss. Just cover
Okay.
through. Yeah.
And we'll see the applications to
In
materials.
materials, yes. Yeah.
Yes. In fact, I'll just make a comment before we stop. Is that I have discussed this IRCR representation, which we used
Yes,
in
yes.
our diffusion model. I have shown them that picture. So that is one of the ways a material can be represented as an image. There are other ways, of course, but that
Yes.
is one way it can be represented as an image.
Yes. Yes. So yes, so if materials can be represented by image, diffusion works directly on it. If you think it can be represented as graphs, now we have graph-based diffusion models as well. So in both the ways, material generation has been attempted. So yeah.
Yeah, and also just one line is that these topics are advanced, so we don't expect you to
Yes.
able to implement or apply these things right now, because these require a lot of reading and learning and coding. But this is to expose you to the ideas that exist and the direction in which application of AI in materials is progressing.
Yeah, well, otherwise this is a, like at least 2 weeks of material. So well, I'm
Yes,
also not doing justice to like giving a full detailed output.
yes.
So don't go in that sense. Yes, just to make sure there's something like this exists,
Mm.
which may be useful in probably in your PhD in future. Yeah,
Yeah, in
yeah.
future. Yes.
Okay. Yeah,
Okay.
fine. We'll see you on Friday. Yeah. Oh, sorry, Sulagna. Can you hear me now?
Yes, sir.
Yeah. Yes, you have some questions regarding the exam pattern. Can we email us? Yes. So what we will do is we will basically most likely send you this weekend, like by the end of this week, that what will be the pattern of thing. We have already emailed the time and everything to like all the deans of various institutes. But exam patterns we will mail maximum by Friday. Yeah. Okay. Any other? Okay. Okay. Thanks. 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 Okay. I'll see you on Friday and we will try to mail you the pattern on like by Friday. Okay.